In this section, we're going to look at cell potential. So how much energy can we actually get out of these amateur batteries? All right, so let's talk about how much energy these reactions have. It's important to say right off the bat that these reactions can only move spontaneously in one direction, just like we talked about spontaneity last time. Electrons are only going to spontaneously flow in one direction, from higher to lower potential, right? From something that has a lot of energy to a more stable, less reactive final product. So if something is spontaneous, though, we are going to say it has a positive voltage. If it's non-spontaneous, it has a negative voltage. Okay, so that's different than delta G, and it's worth keeping in mind and practicing with as you get ready for your exam. Now, what we're going to say about voltage is that voltage is not a measure of the total amount of energy. It is just known as the energy per second, essentially. So it is the energy crossing through the system as electrons are transferred. So it's important to note that when we look at putting voltaic cells or batteries together, they always involve two reactions, a reduction half cell and a oxidation half cell. Now, because these things cannot be separate, it's important that we can't just discuss the amount of energy created by a half cell alone, right? It's always in comparison to what it's paired with. So what they needed is a half cell to stand in as a zero, right? Something that is not easily reduced, but something that is not easily oxidized. And so what we do is use a standard hydrogen electrode or She. In which case we have H plus ions react to form H2, right? All of these half cells we are going to write as reductions, even though sometimes they're oxidations. But what's nice about this is that it's pretty easy to standardize. It's pretty easy to get exactly 1 molar acid. It's pretty easy to get 1 molar of hydrogen gas, right? So it's pretty easy to set the system up and run it under any conditions. But generally, we're not going to use a standard hydrogen electrode at all. We're just using it as a middle point to talk about what is reduced and what is oxidized. What we're going to say is that the more positive the voltage, the more easily that chemical is reduced. The more negative that voltage, the more easily this thing is oxidized, right? A more negative voltage means it's not reduced well, so that means, of course, it oxidizes much better. So here they talk about the strongest reducing agent. Again, strongest reducing agent means the thing that is oxidized the best. Okay, so you can see we've got a whole mess of complicated reactions here. I will point out that most of the metals are down here, right? Metals generally, if you remember back to Gen Chem 1, do not like to be reduced. Metals like to be oxidized. And so most metal reactions like to be oxidized. There are some exceptions. Things like silver is reduced pretty easily, but generally most metals prefer oxidation. I should point out here too, it says at SDP. This means at standard temperature and pressure. So we are also assuming these are all under standard concentrations as well. So these are all standard state voltages. We'll talk about non-standard state in a bit. So it's important to keep in mind when we talk about cell potentials, we are talking about the total energy of the entire voltaic cell. Right? So it's not just whether one half cell is spontaneous and the other is non-spontaneous. It doesn't work that way. We either have a total cell that is spontaneous or a total cell that doesn't work together. So we can measure the voltage of that entire cell by looking at this a couple of different ways. The way I prefer to look at this is the reduction value of the cathode and the oxidation value of the anode combined, right? This is helpful because it looks at the cell as written. The book value of doing this is the reduction value of the cathode minus the reduction value of the anode. These two ways of doing it end up being exactly the same, but if you're switching back and forth, you're going to confuse yourself. It's easier to pick one method, but I will walk through several of these problems with both. Okay, so let's look at this zinc silver half cell, right? So if you go back to that slide earlier that had that big table of all those values, we see the silver reduction half cell, which you'll notice is written as we see it, silver going to silver, silver ion going to silver, has a voltage of 0.8 volts, which is great. Now, the problem is that the value written on the table is this one, and this does not match the value in our half cell as written, right? This is the reduction. It's in our table, but it's not the half cell we're using. What we are using is the opposite. So, if we flip around this reduction to an oxidation, this gives us the voltage needed for the reaction as written, right? And that's most important, is what we currently have. So if we add together the reduction value and the oxidation value, we get the total voltage of the cell. Now, one thing that's important here to keep in mind is that we do not have to worry about balancing these reactions, right? The number of silvers that react isn't important, because this is essentially a current going through the battery, right? No matter how much silver you have, no matter how much zinc you have, they are always going to get the same voltages. So all we have to do is add those two voltages together and we're done. The book method, on the other hand, says, oh, zinc should have a reduction of negative 0.76 and silver should have a reduction value of 0.8. So let's just do the reduction of the silver minus the anode minus the reduction value of the oxidation. Okay, I find that super confusing because, again, this is not the reaction we're using. It's the opposite of the reaction we're using. So to say, oh, well, the zinc has a half cell value of negative 0.76, I find to be very misleading. When we get to some of these problems a little bit later where we put our own voltaic cells together, I also find this very easy to get confused as to what is your actual reduction and what is your oxidation, and that is a common problem, right? People put these balance reactions together as written here, even though this half equation isn't used in our reaction. So this is why I don't like this method. Mathematically, it's not different. It comes out exactly the same. But it's worth keeping in mind as you set these problems up. So go back to the reduction chart earlier and use those voltages to determine the voltage for this voltaic cell here. Okay, so we have a nickel ion to nickel, so that is a reduction. If you look up that value on the chart, it's got to be negative 0.28 volts. If we look at the zinc as an oxidation, as we said before, that's going to be positive 0.76 volts. Again, the table shows it as negative 0.76 volts, but we are not doing a reduction here with zinc. We are doing an oxidation. So the total voltage of the cell will be 0.48 volts. For the book method, it is much simpler conceptually. You just say, okay, well, nickel's reduction, so I'll grab the reduction value. And then I'll go to the zinc, grab the zinc value, but that's our oxidation, so I just know I have to subtract the negative 0.76 from 0.28 volts. It still gives us a positive spontaneous voltage of 0.48 volts. Again, when it comes back to describing what's going on in this equation, I think that makes it more difficult. But if this works for you, that's fine. Okay, go ahead and try this one. Again, it's in the half cell description, so you have to break it into two cells and then use the standard reduction potential list on the previous slides to figure out the voltage for each cell. Okay, so for my method, right, I'm going to say, okay, well, aluminum's my oxidation. Again, the oxidation is usually the first one on the left, but it doesn't have to be. My silver would clearly be my reduction. So if I go to the table, aluminum is a negative 1.66 volt reduction. But I'm using it as an oxidation, so it's going to be positive 1.66 volts. Silver, as we've said before, is a positive 0.8 volt reduction. So we can just add those two voltages together in my method to get a voltage of 2.46 volts. If we're using the book method, we just say, oh, silver reduction aluminum oxidation. So aluminum is negative 1.66 volts, silver is 0.8. So I'm just going to take my reduction minus my oxidation to get 2.46. Again, the problem people run into, and we'll see this on the next several slides, is that people tend to say, oh, well, it's aluminum and silver are the products, and it's not. It's going to be aluminum ions are the products and silver metal. Again, this reaction that shows this reduction is kind of a lie here. We're actually doing this half reaction. Okay, try one more. The issue here is that that first half reaction is a little ugly. We're saying oxygen and H plus are products, and so you should be able to balance it quickly, but it's just a little weird to look at. And then the bromine is a little easier, and then look up the standard voltages and figure out the overall E cell voltage. So here's how I'd solve this problem. We have hydrogen peroxide going to O2 and H plus. To balance the H plus, I had to double it, which means it's a 2-electron process. It also means it's an oxidation. So if you go to the initial voltage sheet, what we find is this, the exact opposite. Since the sheet has the voltage at positive 0.68 volts, the oxidation we're looking at must be negative 0.68 volts. For bromine, we have bromine being reduced, so it's a gain of 1.06 volts. If we add those two together, we get positive 0.38. Now, I did not solve this problem using the book method, but you should get to the same answer.